All right, let's get started. Welcome to lecture 7, Robotics 311. Today we're going to review the thermal stuff we did last lecture. We're going to kind of transition a little bit to a bit of a different kind of topic for the class for a little while. We're going to switch from speccing a system to making it. We're talking about making that system. And that's going to coincide with your labs kind of starting to transition into building your actual setup for your ballbot. So we do thermal review, begin making, talking through a little bit about like a higher level perspective on manufacturing, and we'll get into additive manufacturing. And as we get to it, we're going to have you do a quiz at the end. Any questions before we get started? Awesome. Okay, so like this is where we were kind of like ending our original kind of design framework for speccing the system. We talked through each of these. Last lecture, we really kind of focused on assessing the thermal properties. And we're teaching this to you because, one, it's important, especially for systems like ballbots that care about their mass, and mass properties are going to matter. And then also, this gives you an underlying understanding of the physics going on that governs like actuator use in robots. And so even if you don't necessarily take every design you do to like as detailed a possible analysis on this as you can, understanding the underlying mechanics I think is valuable enough for us to spend this time. We talked about two types of heat transfer. We talked about conduction and convection. And what was kind of nice about these is that they really had the same governing equations. So they're two different physical processes, but they actually mathematically are modeled the same. And we can sort of think of them as essentially the same mathematical process. Conduction, heat's flowing through usually a metal conductor, and it's heating up from a heat source. And then convection, it's heating the ambient air around it, which is causing transfer of heat energy. We went through like some general equations for conduction, where we talked about this conductor. We derived its thermal resistance in terms of its parameters, and those parameters had to do with a couple things. One being its shape, so what is the size of this system, and the other being its thermal conductivity, kappa, which was what? Like, where does that come from? Or what determines thermal conductivity? Let's say you care about thermal conductivity. What does that also mean you care about?
The material?
The material. It means you care about the material properties. So like, if you care about thermal conductivity, then you're going to care about things like metals that have high thermal conductivities, low thermal resistances. We talked about convection, which kind of had a similar rationale. Also related, it has a thermal resistance, which means it's losing heat energy through this resistor, and it's also a function of the shape and interface properties defined by the heat transfer coefficient H. We talked a little bit about how depending on the two different properties that are used, or if the ambient is a liquid instead of a gas, that really affects this, and we can talk about changing our thermal resistance by using heat sinks, which is super common. And we might end up heat sinking your motor drives, we're not sure. The version we use these motor drives in our lab, same exact motor drives, and we heat sink them because they will get warm. Kind of last property we talked about was thermal mass, which we modeled as a capacitor. And the thermal mass or thermal capacitance describes an object's ability to store heat energy as a change temperature. We can store energy lots of ways. One way we store it is by changing temperature, like stored in the mass of a system. And we talked about that in terms of this capacitor. And we discussed that voltage was analogous to temperature, so it's an effort. Current is analogous to heat flow. Trying to think of a good question there, but I can't think of one right now. But yeah, this is the electrical side for capacitance. It's the mass storing heat energy. It would be like a compressed spring. I showed you this example in Simulink and we kind of talked through it. How many of you opened this file not in lecture? Anybody look at it? This is a good file. You guys should look at this file. What could you do with this file? Let's say you cared about this and you're building a robot. What could you do with this file? What does this file allow? What is it doing here? Somebody from a mechanical engineering background should be able to answer this because they've seen it. They've seen these things. What is this? Like, can you guys read this? Yeah.
Isn't it simulating like the temperature that the entire motor is going to get compared to like if we're estimating its resistance for the convection and the conduction, it's going to simulate the entire heat of the windings and everything.
Simulate the temperature rise. Where did this come from and what does this represent?
The movement of the motor.
What?
The output of the motor. So on, off, like it was walking.
It was walking. Yeah, this was like a prosthetic. We were talking about this in the context of a knee prosthesis. We were speccing its behavior and doing steps. So we modeled that behavior as a time that it's on and a time that it's off. And then we just continued it forward in time for a long time to really see how its temperature changes. And then these are transfer functions, which is a simplified way of doing the system dynamics, of modeling the system dynamics, not because they're transfer functions, because of a specific way that I've written it. I've done the math here. That's okay though. I would say this is a simplification that just makes it a clean Simulink model. So I think you can use it. This is what you would do is go in here, you go into these blocks. They only have two parameters. The numerator, which is going to be the thermal resistance, and then a coefficient on the term that has the S. That's the thermal time constant. And so that will allow you to simulate the rise in temperature of a system, of your motor's windings and its housings. Is this an inverse model or a forward model? Forward model. How do you know it's a forward model? Because we're solving an ODE forward in time. So inverse model doesn't use Simulink, for example, just like we didn't need Simulink to do our modeling of motor current and voltage. So this is a forward model that's saying, okay, if I know the heat flux, or I know the current that's being provided to the motor, what could I expect my windings and housing to increase in temperature, given that I know the I squared R loss? Yeah, this is something it's commented. You can use it by kind of pattern matching, by knowing that that's the thermal resistance and that's the time constant. So those are kind of written there. But that's a good M file. It can be very helpful to look at this temperature rise stuff. But we talked about how you guys might not care that much. So that type of analysis is really useful. You're really trying to exploit this difference in the delay. So when you heat something up and it takes a long time to get to its steady state temperature, if you exploit that with something like this analysis, you can design systems that are smaller and push their actuators harder. So you might not want to do that. You would do that if you care a ton about the mass. So you're working extra hard for something like 10 to 50 grams. But in this project, or generally, you probably won't care about it quite that much. And a steady state analysis can be used, which is what this was. That's what you did on your quiz. So in steady state, we know that the capacitors will no longer receive any current, and the system reduces to just a series set of thermal resistors, and we can use Ohm's law to determine their temperatures if we know Q. If you look at motor data sheets, oftentimes they include information for this kind of simplification, and that would be the continuous values. It might provide a continuous current or a continuous torque. So it's giving you the information to do this shortcut. Cool? Does it make sense why we learned this, what it can be used for? And then in this class, we did this. That's when we were speccing this motor and transmission pair for your ballbot, we did this analysis. And we can also tell that it meets the continuous current specification. Okay. We're gonna kind of like review that just real fast, and then we're gonna transition. Okay, so in order for this design framework to to work, I kind of want you guys to help me understand, what do you need, what do you have? So what are the parameters that govern a transmission? Ratio?
Efficiency.
And it's efficiency. And you need those, yeah? So those are things you have to find. You have to look up, or you have to have some understanding of it. How about for the motor, what do you need?
Current and voltage.
You do. You need, so I'll come to that. But what are the parameters that define the motor?
Requirements?
Inertia.
Torque is in there, but I'm gonna say,
Inertia.
yeah, resistance. R. It had inductance, which we call it L. Torque constant. KT. Inertia. We call it J. And damping. We call it B. So you need a bunch of parameters. So this is what you need for the transmission. That's what you need for the motor. The motor's got a lot more parameters. Requires you to look up a data sheet. Where do we get the motor parameters that we're using for the ballbot? So that link is in the MATLAB script that you guys were provided. Thermal properties. What do we need to know for thermal analysis? Yeah.
Thermal conductivity.
We could, so that would be if we were like trying to derive the thermal, what we really need to want is thermal resistance. If we were doing thermal conductivity, that would be what's kind of inside that thermal resistance. It comes from the thermal conductivity. But we don't usually, we try to not like know that or get to that level of modeling. So we need thermal properties. Which could be resistances and capacitances or time constants. What do you guys choose? I have 3 things. Maybe 4. Yeah.
Velocity.
Yeah, so we'll say, I'll call that application requirements. Which is gonna be an effort and a flow. So it's torque and a speed, set of specifications of some kind, a trajectory, something that says you know what it's gonna do. So application requirements, what's next? What's another one? What else do you choose?
Current and voltage. Oh, I guess that's effort and flow.
Yeah, I'll say max current and voltage. That's definitely something you choose. And the other thing you choose is motor and transmission ratio. So what the intent of this slide was to quickly go over the symbols, what you're typically provided with, and what you typically have to choose. So this, remember the name of the game is to make these choices and make them well. Okay. So let's move on. After this, so here's our framework. This is what we would say is speccing. So we went through this speccing process. And that happens first. So this gives us torque and speed, ratio, sizing information. So we know something that we kind of know what we want to build. And now this is going to be the focus of the class for a few lectures, a couple weeks. So physical design, we're gonna talk about layout, we're gonna talk about manufacturing. Yeah,
What did you write under ratio?
sizing. So if you have if you've selected these things, if you spec the system, then now you not only know what it needs to do, but you also have some information about its size. Size of the motor, size of the transmission ratio, all that's gonna factor into its size. You have some idea of its size, and you have its specifications. Now when you talk about physically laying it out and making it. So this includes the physical layout, solid modeling, creating design files, and manufacturing. We're going to go over manufacturing first, because we're getting into that in the lab. There are three types of manufacturing: formative, subtractive, additive. We will focus on these, some of this. So formative means we're creating a mold typically. So we might do an injection mold or a cast. Subtractive is we're usually milling or lathing. We're going to cut a part out of a block of material. And additive, we're going to create a part from no material, from a different type of material. We're going to build the part up. We're going to focus on subtractive and additive only in the context of rapid prototyping. So we're not going to talk about all types of manufacturing, or at least just touch on it. We're mostly going to focus on the things that you would need to build rapid prototyping robots. Okay. The choice for subtractive versus additive is driven by many factors. A lot of it has to do with sizing, the size of your features, the size of your part, material properties, loading conditions. We'll kind of step through these. For rapid prototyping, the focus of this class, we would want features that are probably on the order of tenths of millimeters to hundreds of millimeters. So if you're going to use rapid prototyping, or three different types of rapid prototyping techniques, features should be on the scale of 0.1 millimeters to hundreds of millimeters. You get common materials from these approaches, including plastics, woods, ceramics, and some metals. And it allows you to iterate fast. That's the idea, which you got made obviously because of the name, but that's the game, is that when you can iterate really fast, you can actually like move projects much faster than they would previously be able to be moved forward. Subtractive, we're going to kind of like quickly touch on milling, lathing, and what we'll talk more about is laser cutting. Oops. Laser cutting and water cutting. Additive, we're going to talk about 3D printing. It depends, the type of 3D printer depends heavily on the scale. There's also all sorts of, 3D printing is a huge area of research. There's all sorts of really neat new 3D printers being developed, but mostly on much smaller scales. what we're gonna talk about, or the type of 3D printing we're doing is now like a commercial product, and it's very robust. This is just a quick little schematic I found from a paper. And what was kind of cool was this part. This is just quickly showing differences in subtractive versus additive, but the real difference is the waste that it produces. So subtractive manufacturing often produces a ton of waste, especially when you're making parts like what we're creating. It would be generally milled out of a giant block of material, and that just creates an absolute ton of waste, whereas a 3D printer, it's only building the material of the part, and it's potentially its support material, much less waste. And there's a lot of people studying how to bring the waste of traditional manufacturing down. That's kind of neat. Yeah.
For the first line, it says choice for subtractive versus additive is driven by what factor?
Many factors. We're going to kind of go through some of them. You're going to kind of learn them by that's still hard to read, by the attributes, by many factors.
Thank you.
Okay, for example, so this is advantages and disadvantages of 3D printing. I said it's an active area of research. These are some diagrams describing kind of motivation for additive manufacturing. I put this, it's a textbook chapter. I downloaded it and put it in Canvas Resources if you're interested to read more. It's actually pretty readable. I don't know that it's the best textbook chapter ever, but I figured it couldn't hurt to share with you guys. This is describing some of the differences between additive manufacturing and traditional manufacturing. Traditional manufacturing is in red. So this is saying that the further you are out on this kind of spider web, the better it is. So size range, traditional manufacturing doesn't have any size constraints or very limited, so that's better in that sense. But for example, lead time, additive manufacturing will be faster generally. So this kind of describes qualitatively some of the features that go into the decisions for rapid prototyping. If you're trying to iterate quickly or trying to do something that doesn't have a ton of logistical burden, rapid prototyping or 3D printing is a great way to go. As an example of the research going on, there's over 10,000 publications each year now with additive manufacturing. That's a 300% increase since 2015. So this is neat. And there's a lot of cool research going on at Michigan in the mechanical engineering department, people who study additive manufacturing. So what accelerated 3D printer development? Why all of a sudden now is it we're saying, oh, it's actually really easy to get stuff made this way? What changed? And this wasn't true, for example, when I was in college. Well, we improved the quality of components. The improved component quality and availability. So this would be, for example, the stepper motors that drive a 3D printer, or the electronics, or the filaments. What else? There's like a couple other things. What else do you think? Yeah.
3D design software.
3D design software. So better, CAD, like SolidWorks, open source CAD software that you can do in your browser. You don't have to, there are other competitors of SolidWorks. They're much lower in terms of what they can do, their capabilities, but they're available. There's open source. Yeah.
I'm not sure if this would be one, but better plastics.
Yeah, I'd say I would probably consider that I'm kind of considering that here. Better plastics would be like improved component quality, but that is definitely true. The third one is actually that this open source concept, and that the patents, the original patents that were protecting additive manufacturing expired. So open source versus open IP. So this, all of a sudden, when those patents expired, it let people begin to develop with that intellectual property without the fear of being sued. Yeah.
How long was additive 3D printing or additive manufacturing done when it was patented? Like how long ago did it come out?
In the 80s, I think is when they're
It was like
patented.
really bad because it was so protected.
It was, I mean, it's just one of the, that's kind of how the US science and tech innovation world works. It's like the kind of benefit of them thinking of it first. So they get 20 years, I think, of protection. But then it expired and now we all get to use it, which is great. So then this is describing a little bit about like complexity is on this x-axis, cost is on the y-axis. This is traditional manufacturing, this is additive manufacturing. It's sort of saying at very low complexity, it might make sense to do a traditional machining process. That could be true. I don't think I think pretty much it's hard to make it any cheaper than additive manufacturing, at least what you guys have access to. So I think that this is actually like come down some still. So I'll say AM. Let's come down in price further. So what this is really saying is if you have a really complex part, additive manufacturing is going to be much, much better due to the machining time associated with machining complex parts. Why would machining a complex part take time? It's because this is the machine that's typically used. So this is a mill. This is a traditional manufacturing tool. The way the machining is done is it's completed by a spinning bit. What's that bit called? Anybody know? Like end mill. So it's an end mill bit. Looks sort of like a drill bit. It's right here. So that's an example of a part. Yeah, this thing is spinning. This is a part and it's milling out the features by changing its X, Y position, but it also generally changes its Z position and it can do very complicated parts. So hopefully, or maybe this will make sense. Depending on the part geometry, it can make milling harder or easier. So it factors a ton into design. There's generally two types of mills, 3-axis versus 5-axis. That means how can this part move? 3-axis means it can move in X and Y and Z. 5-axis means it can move all around. So a complex part, so here what we have is a part shown that's calling out a few of the different concepts that exist when you're thinking about machining something on a mill. So this cavity, this is a cup. End mills are sensitive to how deep they are. So when you're cutting at the end of a long bit, they deflect and it causes bad surface finish, cause other sort of challenges in manufacturing. So depth of the part would be a challenge here, or could be a challenge for it. So if you're building a part and you want to have an end mill, you have to be careful how deep are things getting. Also, this is an undercut, the way that shape is coming down, which means if it were fixtured and a mill is milling it out, a 3-axis mill cannot mill under there because it would run into the side. So that, as soon as there's an undercut like this, it requires a 5-axis mill. So this part could not be machined without a 5-axis mill. 3-axis versus 5-axis. This factors into design. 5-axis mills are more expensive. So parts made on a 5-axis mill is going to be more expensive than a part made on a 3-axis mill. This is an example of a multi-axis mill here. That's kind of what they look like now. They're like these little rooms almost. So you have to watch hole depths, undercuts, radii. It also is saying, so this call out is saying that if this was milled, and a mill bit is kind of coming around here, and they want a sharp corner, for example, where that handle meets the side of that cup, if it's being milled, can it produce a sharp corner there? There's no way for it to do that. It will always run up against the radius of the bit. So like this would be called out to you. If you tried to have this machined, a machinist would call back out to you and say, this cannot be machined, or this needs a radius. So that's another kind of thing. Each one of these is talking about those general features. And then the last thing is that the base would have to be fixtured. So it couldn't be milled because something has to hold that part to get all the way around it. Yeah.
So if milling has so many issues, like when would you want to mill something as opposed to 3D printing it?
Oh, okay, yeah. So I actually, we mill everything. So I would not, it does have issues, but if you don't mind paying for it, it's not a big deal. So it just means that when we build parts, we barely consider these things at all. And we just already know it's gonna have to be machined on a 5-axis mill. And then if you think of it that way, it doesn't really constrain you much. But we also machine with traditional manufacturing methods because we need the strength provided by metal parts in our work generally. So anyways, yeah, this just kind of shows you a little bit about milling. I just want you to be aware of this. This isn't really what we're focusing on. These are traditional manufacturing methods. In addition, the other one I want to mention is lathing or turning. So lathing is similar, except for that the part is spinning and the cutting surface moves at a radius. Cutting or shaping with a lathe, which is what this is. It's completed by rotating a part and cutting at a radius. Other uses, woodworking. Anybody here a woodworker? Yeah, so woodworking uses lathes. It's easier, like than a metal part. Okay. So when you think about, so a lathe is just spinning this. It also can be controlled manually or via CNC, computer numerically controlled. So whether you have to give it, actually move it, or it does it by itself, but it's spinning apart and cutting at a radius. So once you kind of begin thinking about what are the challenges of traditional manufacturing, you can start to think of what are ways that I can design to take advantage of what rapid prototyping enables, and we're going to do that in this class. So design decisions can be made to take advantage of rapid prototyping tools. So we're using laser cut acrylic to take advantage of those, how easy that's going to be. Another thing I wanted to kind of mention before we get into the actual 3D printing is tolerancing. Tolerancing defines how parts fit together, so the intensity of that part's physical mate. And when you have a part machined and you're buying, so traditional manufacturing, you might be buying bearings or drive shafts or something, those parts will have a tolerance, and the part that you make has to meet with that tolerance and it has to have the fit that you want. We're not going to spend a lot of time on that in this class because we're not really doing metal parts. We're not going to worry about fits that are that tight or that are that, we're not that meticulous about our fits. But I want you to know that this is a thing. Tolerancing exists. It's if you're designing a traditional manufacturing, you would have to care about it. It really comes into play for bearings and shafts. What I want you to see is this ISO standard. So when you make a part, let's say you're 3D printing something, you might 3D print a shaft that you want to spin in something. So a shaft that you want to be free. How would you do that? Or like how do you think that would work pre this lecture? Who's 3D printed something before? Who's 3D printed something that had motion, that had parts that moved with respect to each other? Did you have to do anything to ensure those parts would be able to move? Who did? Yeah.
A little gap between so they
Add a
can move
little
freely.
gap. What gap did you add? Or how did you know what gap to do?
I just eyeballed it until it worked.
That is the fair way to do this. My guess is that you would be at like kind of like tenths of millimeters. So you might need between 1 and 2 tenths of millimeters on the radius to give it the ability to spin more freely. So another design consideration is something called tolerancing. Typically, tolerancing is provided on an engineering drawing where you might call out what the range of allowable values are. What I want you to see is this ISO standard. This is saying, so this is a little table. The whole table is uploaded to resources, Canvas resources. It describes, so this is kind of a nominal dimension. And this is for linear dimensions. So this is like translation up to 3 millimeters, I think. This is up to 6 millimeters. And what this is saying is any dimension that's kind of like between 0.5 millimeters and 3 millimeters, depending on the tolerance class, medium, fine, medium, coarse, very coarse, they have an allowable amount of millimeters that they can have error. And the machinists that we use this fine class. So this is telling you, for these parts, they want kind of plus or minus 50 microns to be considered a fine tolerance. We just said for 3D printing, you're gonna want hundreds of microns between parts to allow them to rotate or move. So this describes an ISO standard for machining parts. It should give you kind of a gut feeling for what fractions, if this number compared to this number kind of tells you the error. And so as parts get bigger, you go down this chart, parts get bigger, the allowable error gets larger. It's sort of a percentage of this nominal dimension. But this kind of tells you, at just a couple of millimeters, you're at for a fine tolerance, you're within 50 microns. For a larger dimension, something like up to 120 millimeters, if you're within 150 microns, they would consider that fine. Yeah.
So, like, what sort of fit is this chart supposed to provide? Would it be like an interference fit or a press fit or something else?
This uses a class of fits that's called maybe a locational clearance. So it's not, so there are different, within tolerancing, there are these different class types. For example, interference is one. That means that the tolerances of the kind of male and female part will be overlapping, meaning those parts could physically interfere. If anything interferes, it will not assemble. But we never ever use, and I would generally recommend never using a press fit or a interference fit, because we don't really ever do anything that requires that. You have to heat it with, like, assemble it with a heated press or something to make that work. So we use what would be, I think, generally in the machining world, pretty loose tolerances. Locational clearance, or sometimes called transition sliding fits. And so these classes pertain to those types of fits. So what I wanted you to see is, like, if you go to this page in Canvas Resources, it'll have all the different types, rotational or angular tolerances, linear tolerances. It'll kind of give you this information that is what I would say is the state of the art right now. Also, like this book, this is a machinery handbook. It's awesome for building machines. It's a good reference guide. It has tolerancing in it also. All the same information. It has little pictures that kind of show you kind of where the allowable tolerance ranges are, when they begin to overlap and becomes interference. So that's a great book. Okay. So that was kind of the beginning of manufacturing that we talked about. There are kind of these two really common traditional manufacturing methods. Now we're going to kind of move more into additive manufacturing. When you create a file, so if we want to 3D print something and use additive manufacturing tools, we have to go through a couple of steps. What we just talked about is kind of, we have a design, we maybe have a design in SolidWorks that you're building in your labs. And what we want is a finished physical object. And like, what are the steps that we have to go through to get there? The first step is to create an STL file. So to use a 3D printer, first a part is needed that's exported as an STL. The STL file contains polygons that digitize the shape. So now the shape, it no longer becomes the kind of smooth SolidWorks model you're used to seeing. It becomes a digitized version of that with polygons that make up the part. More polygon elements mean more detail and larger STL files. Usually they're between kind of the kilobyte to megabyte range. So when you'd have your part file, you go to SolidWorks, export, STL. Then you get to choose kind of this level of detail. That's up to you and kind of the part you're designing. I usually generally do relatively high levels of detail. That STL needs to be converted into printing instructions. Known as, who knows what the printing instructions are called? Yeah. G-code. So we need something to convert this STL into G-code. And what we used for that is a slicing software. It's more likely that in this class, slicing will not be done by you guys, it'll be done by Alyssa. But I'm not sure, since we've never done this before. I'm not sure if she'll do the slicing or if you guys will do the slicing, but we're gonna learn about it either way. And then this kind of shows some different polygons. So this would be a sphere, and this is just two different levels of polygons. Okay. What is G-code? G-code is it's a file, it's a text file, that's a series of commands that tell the 3D printer how to print. What might be in there? What would be in G-code? What's the information? You have an STL file. I think you guys generally get what that's going to be. I think you know what a 3D printer is doing, sort of at least globally. What is the G-code actually giving it?
It's giving it like every instruction, so like when to extrude, how much to extrude, X, Y, Z, and temperature of everything.
Yes, it's giving it all the commands for toolpath, the speed that it moves between these, the temperature of the heating elements to extrude the filament. So it tells us all the general instructions. Each 3D printer expects G-code to be formatted a specific way based on the printer's firmware. There are two major classes of firmware on a 3D printer. Two of the most common printer firmwares are rep. I'm just gonna write that bigger. Rep and Marlin. So these are the different firmwares that exist on different printers, and the slicing software exports the G-code in a way that whatever printer you're using would understand it. You go select when you slice it what type of firmware it's using. This is an example of how it reads G-code. It's actually really, really straightforward. This is an example snippet from G-code. If you look at it, it might be like 10,000 lines long or 100,000 lines long. All the instructions to move the printer, and it's readable. You can actually open G-code and look at it and tell what it's doing. And you could also write a text file directly that commanded your 3D printer to do something. Also, a key function that slicing software provides. It provides information on infill pattern and layer height. Infill is exactly what it sounds like. It's the pattern of interior/structural plastic. These are different infill examples. So like it can be really coarse, no infill, really coarse, and then really fine. And the infill is going to change two things mainly. And they're obvious. What will it change? Strength. Thicker infill for parts with greater loads. What else does it change? What? Flexibility, yes, that's on there. It will change the part's flexibility. Something else important. Mass. It's gonna make the parts way heavier. So we have like a ballbot we're making with acrylic plates and then a motor mount. You guys are designing the motor mounts. What infill do you think you want in the motor mounts? A lot or a little? A lot. So the motor mounts are gonna be infill with time. I think we made ours solid. Is that true? No. What's our, do you know, remember the infill position?
57, 50.
Okay. Okay, cool. All right. So just a few examples of infill. And then the slicing software, so let's say you have your part. It's gonna figure out how to do the infill based on what you tell it, of what infill percentage you want. And then it's gonna understand the geometry of that part and mix the infill such that it all connects and is happy and structural. So different types of infill based on part geometry. And all this happens automatically. So it creates infill in addition to the toolpaths to create the infill. It also selects or also specifies the layer height. Print speeds, so this also happens kind of in the instructions in G code, in the slicing software. The print speed can be optimized based on the type of material it's printing, and that's all already done for you. So it goes, they're trying to a huge area of research also is maximizing the speed of 3D printers. The most common open source slicing software is Cura, provided by Ultimaker. I don't think you guys will have to interface with that at all. I just want you to know that it exists. Okay. I have like 8 slides or so on these 3 guys, and then a couple of slides on best practices. We have 30 minutes, but I'd like to give you a quiz. I also think this lecture is pretty information intense, or maybe like a little boring. So why don't we take like a 5-minute break or something, and we'll come back and I'll do these, we'll see how far we get, and then we'll do this quiz. Okay, 5-minute break.
Cause I got
We have to go to
you can't solve it. Actually, I'm over the number because I mixed up my thetas. Like one of my thetas is like
Tomorrow.
polar axis is but it's maybe that's right.
Like how far? Because we have like.
Class.
Like in the textbooks, we have problems. Oh, right. Yeah, like we have example problems, and usually those, like if you have a hard problem like that. That's what I always do.
I haven't read the textbook at all, honestly.
I don't read the textbook, I just look for those problems and how they say it, and just do it. I feel like setup is the hardest thing.
Yeah.
Every time I start another like quiz, to remind myself that you just split accidentally. Like all 4 questions. And then after that, it's like pretty okay.
Yeah. It's really just refreshing.
Yeah. The I still don't know why they do like that. Yeah, it's a little nonsensical to me. I feel like rotation matrix makes more sense.
Yeah. I think we just maybe
I think I only have math 216, which I guess you do linear stuff in that class.
yeah, I think it's really dumb that linear isn't a direct for 216, honestly, because
Yeah, it's all linear.
like, literally, exactly. Throw all the eigenvalue shit at you and just expect you to learn it. Something like that.
Slides.
Yeah, so you're so
Yeah, no, you're right, it's basically just a rotation matrix. I think they just didn't want to say it like that.
I feel like it makes so much less sense when they don't say it's a rotation matrix.
And like there aren't supports that you can hear either.
I don't think I learned anything, it's just like how.
It's just
So you actually were
First thing works with that.
Oh, but
I knocked that out like maybe
What is it about?
but this one's tricky and I don't really want to do this one.
and then also isn't there MATLAB stuff?
Are you going to like present something or?
No, it's just mainly going to this one.
No, last week because I just felt really behind, so this week I'm trying to like get everything done super early.
Yeah, I think it's literally like Tuesday.
Exactly. But usually I'll have like all of my homework done by like just chill on the weekend.
Wow.
I'm a little bit on the grind side this year.
It's crazy going to office hours and stuff.
Literally. No, that's serious. I literally never used to.
All right, we're gonna keep going. Was that enough time to give everybody that helpful? All right, let's keep at it. Only like 5 or 6 more slides. Okay, the next 5 or 6 slides, I want to tell you about 3 types of 3D printers, and then a slide or 2 on best practices. I think everyone's probably heard of FDM printers. Anybody not heard of an FDM printer? Okay. Really?
This is the normal video?
Yeah, fused deposition modeling.
Okay.
My guess is you have. This is, I'd say, the most common type of 3D printer called fused deposition modeling, and it is generally used to create plastic parts, and then the size and quality can go anywhere from like very small $100 systems to very large, really, really expensive, $100,000 or $10,000 plus systems. So this is one of the most common types of 3D printers. Heated plastic filament is fed / extruded through a nozzle. Common plastics, ABS, PLA, nylon. It's common plastics you would use. It builds support material alongside the material used for the part. Build material, so let's see, support material alongside build material to support parts as they print. Costs hundreds to thousands. So here's a little depiction of this. So we have support material and build material. Build material is blue here, support material is red. It's fed through this 3D printer. It's heated in a giant block of metal. Heat liquefies the plastic and it extrudes it into a CNC pattern and just builds it up. I think you guys know this. This is the most common and what we'll be using mostly for this class. Layer thickness, there's a few categories that 3D printers are kind of measured by that govern their performance, governs their cost, that governs like the way the part will look and act. So layer thickness for FDM printers can be something like 0.1 millimeters to 0.5 millimeters. So that's gonna be, it's gonna lay the part up, squeeze out the material. That's gonna, when it finishes, the G code will say, start next layer. It'll, the part will move, or the platform will move, it'll just keep going. Build volume, these are probably like 10 by 10 centimeters squared to 50 by 50 centimeters squared. Materials we'll talk about in the next slide. Then the FDM printers have a pretty cool, like recent innovation, and that's that you can make them composites. And what's really cool, you can make them continuous composites. Versus chopped fiber. So as it's printing, some printers, we'll talk about this more in a slide or two, can lay a fiber with it, and that's going to help the strength of that material. Chopped fiber is not nearly as good. I don't really even consider it an innovation. but the continuous fiber is a huge deal. That's really good, so we're gonna talk about that more in a second. So this is FDM printers. Here's an example of $800 Prusa. We have a handful of those downstairs. This is a Mark Forge printer. This is about 50 grand. This is the kind that can do the continuous fiber. This is also downstairs. This is something that we own in my research group, but the building also has access to it. So it's not in the makerspace. It's in the other building. So it creates parts that look something like this. They're beautiful parts, very high quality. We almost never use the continuous fiber. But when we do, it's really nice to have. Okay, the different materials, we're gonna go through them for FDM. This is a cool little schematic I found on 3D Hubs. There's tons of information available on 3D printing online. So this is one that I thought was really nice. It kind of talks about the different materials used in FDM printers and some of the kind of attributes of those materials. Ease of printing, visual quality, max stress, layer adhesion. These are the kind of things that you're going to care about. You can kind of specify based on this kind of chart which material you want. You'll almost always use PLA or ABS. PLA is a thermoplastic monomer. What's a thermoplastic? Yeah.
Is it plastic that can be heated, handle
Mhm.
heat?
Yes, and that changes material properties, and then when it cools, it changes back. It's a thermoplastic that is easy to print. High toughness. I think it's sustainably manufactured. Sustainable. So PLA is awesome. Great material. Yeah.
What did you write after thermoplastic?
Monomer. ABS. Also a great plastic. Everything we use is basically ABS or PLA. ABS has better temp resistance. Compared to PLA. And I think it's manufactured non-sustainably. Strong, non-sustainable. It can be post-processed with acetone. Does anybody know what that does? Post-processing ABS with acetone? Makes it smooth. Yeah, it makes it sort of like if you put it in it's called an acetone vapor bath. So you take your part after it's printed, put it in a little container with a cup of acetone, and that'll evaporate into the air inside that, and that chemical will smooth out the print. And it'll improve the layer adhesion as well. So that's something that people do with ABS. PET is heavier than PLA, than ABS, but it has high chemical resistance. So you can see like some people might care about that, it has some uses. And then the other is nylon. So strong, some, again, isotropy, what's that mean? What does isotropy mean? Yeah, anybody know?
It's like the quality relating to direction.
Yeah, it's whether the properties of the material are consistent across dimensions. So if that's true, we would say it's isotropic. If it's non-isotropic, then its properties change with the direction. Why would 3D printers have non-isotropic properties? Yeah.
You're laying the filament down in one direction.
You're laying it down, yeah, in the XY plane and stacking it. So it has semi-anisotropy. This is mixed with glass or carbon fiber composites. This onyx that we're seeing right here, Markforged onyx, that's their name for their nylon material. So some of these 3D printers manufacturers have a material that they call their material. So onyx is what Markforged calls their nylon. Or it's a nylon-like chemical, and that's what's kind of laid down with the filament. So these are the main materials I wanted you to know. Almost always in this two. Yeah.
What's like usually the most expensive and cheapest of the materials?
That's a good
Are
question.
they similarly priced? It's just preference.
All pretty cheap. Do you guys know? Yeah.
PLA is more cheap.
PLA is cheaper.
Then probably ABS after that.
Yeah.
That makes sense. Yeah, PLA is cheaper. Good question. Yeah.
From the graph, it seems like polycarbonate seems really nice, but I don't think it is used that often. Is there a particular reason?
Yeah, I think I did have polycarbonate actually on here and I removed it. Because I think it is pretty esoteric. I think it's maybe brittle. Do you guys know like what's the downside of polycarbonate? Yeah, I never see it being used. I think it's brittle. I think, it might also be UV sensitive. I don't know. Okay, so this is our $800 Prusa. It creates little parts like this. If we look in closely, you can kind of see not see the well, I guess. Can't really see it at all. All right, never mind. Let's see about the other part. You should ideally be able to tell that part is nicely made. It's a nice looking part. Like a lot of detail on the letters of Markforged. You can tell that's a way, way better printer. So you guys can use that if you want. Okay, this is about Markforged. So I'm showing you this one because I think the Markforged printer is awesome, and two, the way you print is different. And I want to show that as an example. So the way you print a Markforged is it doesn't use a slicing program. You actually connect to it with a browser, and then you can. This is one of the parts for the ballbot. It kind of tells you all the information about the part, and then it would allow you to select reinforcement material. You can kind of select where it goes. So this is kind of how this process would work for the Markforged. This is where we add. Reinforcement. It uses a browser, which is kind of interesting, and it lays continuous fiber. No slicing software. Why does Markforged care about the slicing software? Every other printer, most other printers, you're sending a G-code, but Markforged, you're not. We're going through this browser, we're adding an STL, it sort of took over the slicing, yeah.
Could it be because of the continuous fiber?
It is. So because they need to have access to the way the part is laid out in the printer, because they want to modify it to lay fiber with it. So that's why like this as an example to just show you how a browser-based version of this would work. And highlight the fact that like, okay, it makes sense that they would have to do something like this because they've hijacked the slicing aspect of it to add a continuous fiber. And then these prints, I think these are like bike handles or something, but these show you the different types of fiber they have. It's kind of hard to see like this. But you can kind of tell how it's kind of laying the fiber. So it's really like carbon fiber, Kevlar, fiberglass, and I think they have like a modified fiberglass. But it kind of lays it around the edges. So why? Why do they? because they need to add reinforcement. So yeah, this is what they look like. See it? Yeah.
You want to just briefly explain again, like what you mean by the continuous fiber?
It means like as it's printing, so it's printing layer by layer. So it's got G code, it's giving it its instructions, it knows what to feed material. So that's regular FDM printing. The Smart Forge has another capability, which is in addition to printing support material, build material, you can also like lay out, so feed a long, like spooled piece of fiber. And so what that does is it now mixes the plastic with the fiber, and the fiber can help distribute loads, just like rebar and concrete.
So is it like printing, like this, the approach to it is still the same, but I thought you said there's no like so it's just like coming out at the same time?
It's
and
coming through a separate process, but yeah, in parallel.
Oh, okay.
So there's another spool with the fiber on it. Then you don't have to use the fiber or print with it. We won't use it when we
And it
need it.
just makes it stronger and
Makes it stronger. And you can isolate it. So like for this, for example, if this were a handle, you might want to, like for example, right here would be an excellent place to support.
so you can like choose where, yeah, okay.
You can choose where it goes, but it does the routing. It might give you different selections or options, but it kind of it does the planning of where the continuous fiber would be laid down. If it were chopped, so instead of a long continuous strand, they'd be little bits and pieces already cut up into the filament, and that doesn't really do anything. But the fact that the continuous fiber can take load on one end and transfer it to the other end, that's what makes it really strong. Cool? Okay, so that's FDM. That's kind of all I wanted you guys to know about it. You're going to use it in this class. The next one I want you to know is SLA, stereolithography. This is a really unique kind of type of 3D printing. The way it works is a part is in a solution of a photoactive resin, and a laser basically cures that resin into a solid on the top of this plate. And then the plate descends downward. So wherever the laser is focused, that's where it's going to create the solid part. So SLA uses a liquid photoactive resin. The lasers cures and solidifies a thin layer of material. And then the part descends. So instead of FDM, which builds the part up, SLA builds the part down. So it creates support structure as like a lattice, and then you just break it off. And you can kind of see all of this down here, all of that support structure, it would all come off. What's really helpful about that? We don't have to have a second spool of support material. There's no second material. It's just the SLA. So that's good. That's convenient. All the printers, all the FDM printers have to have a build material and a support material. You're always kind of filling those back up. So do you think these would be expensive, more expensive or less expensive than?
More.
They are actually, but they're still quite cheap. You can buy them for like $100. You guys ever seen those little figurines people are into, like painting? You can buy them and then they print this figurine. You can buy them, the whole printer is this big, and it just prints these little figurines, or whatever is that size. But those kind of SLA printers, those are actually like a modified version, but those are only like $100. It's really, really cool. But they can get very expensive.
Isn't the resin also like a lot more expensive than PLA?
I think that that's true, but I don't know the cost of it. That's a good thing. You guys, do you know?
Costlier, but I don't know how much. But it's
Yeah.
relatively so much costlier than films.
Yeah, because I think it's like up to like 90 for some of the resin.
You can get it on
Really?
like 20, like you like a little tub.
Okay, I guess yeah, if you're doing small, but I feel like for the normal Formlabs Big 3, it like got pricey because like you have to fill the
Okay.
entire tank.
I believe it.
I was gonna say also, I know the resin like gives off like fumes
Yes.
that can be toxic, so.
Yeah, these are also like way more toxic chemicals, definitely. Layer thickness is gonna be about 50 microns. Plus, build volume, can be very large. This one of the benefits of this type of printer is you can make it really large. Materials are all photopolymers. And their photopolymers can actually come in all sorts of different colors and durometers, but the material properties, but they all have this photopolymer concept. And there's different variants on SLA printers, one being this kind of DLP version. So the SLA printers is using a laser, so it's focusing on a single point. A DLP printer is printing an entire layer at once. And those are the ones that $100 one I saw that prints figurines, it's using a DLP. We have 7 minutes. I think I can get through it. So this uses an image, not a laser, the DLP versions. And then the last one I want to tell you about is PolyJet. You guys have just heard of PolyJet printers. They are popular, and I think there's some on North Campus. But they're different. So PolyJet printers print like an inkjet printer. So they spray a material onto the part through a set of nozzles, and then the jets, and then they cure it with a lamp. Cured with a UV light. Invented by Stratasys, one of the main 3D printing companies. One of the things that's really cool about this is that it can print in multiple colors, hardnesses, durometers, so you can make very rubbery parts. And you can make rubbery parts that interface with non-rubbery parts or materials, like aspects of your part. So that's pretty cool. It's kind of like what they're trying to show here. This is what it looks like. The white version of it has this kind of like cream color. And then, rubbery parts, which is really neat, actually. It's really cool. So support material for this kind of a printer is kind of hard to get off, which is annoying. Sometimes it's assisted by an ultrasonic water bath that helps the support material come off. Yeah.
If they're printing with multiple materials, how do they deal with fusing them together?
I don't know, like other than when they spray, like it's a bunch of heads, and those heads have some connected to a different material. When they're kind of printing it, it's just spraying the material part. I don't know, like at the interface, specifically how does that work? I have to get back to you on that. That's like a Stratasys question. But there's probably some information there, but I'm not 100% sure. As it sits, it just kind of is connected to two different, the jets are long, like maybe the size of your finger. There's a bunch of different jets in it. Cons. Their parts are quite UV sensitive. So parts that are UV sensitive are gonna slowly get more and more brittle over time. And eventually they're like you can't use them anymore. So in my mind, that's the major con of this, is it produces parts that get more and more brittle each day, and then they break and, I don't think that this material is a great material. Like the functionality of doing the different durometers is really cool. Yeah.
Is that just due to the material that they're using to spray?
It's an aspect of the fact that it cures with UV light. So like that, because they use that, That means that it gets brittle, yeah.
I was gonna say, wouldn't that make it kind of used because this is the sun have some UV on it, or
What's that?
wouldn't it just like any normal light then like kind of start making the 3D print? So what's the use of this then? If
Rapid prototyping.
okay,
It just creates parts that slowly get more brittle. Yeah, a lot of people still like it. It's good for shorter durations. Or if you paint it, potentially. So similarly, they're very cheap to very expensive. This Connex is 500 grand. Layer thickness is going to be, they're also quite good. Tens of microns plus. Build volume up to 100 by 100 centimeters squared plus. Materials are also photopolymers. So essentially we have FDM, an FDM style printer, that's most common, that's what you're gonna use mostly in this class. Then we have SLA printing, which is pretty neat, but not probably what we'll use in this class, but something you guys should be aware of. And the same thing with PolyJet. So mostly you'll use FDM. Okay, we have 2 minutes. I'm not gonna try to do this quiz or talk about best practices, so we'll come back to that next time on Thursday. So on Thursday, do a quiz, hopefully, we'll do best practices, and we'll keep going, we'll do laser cutting. Yeah.
How far are we expected to be in our like CAD modeling before lab tomorrow?
Good question,
Is there
okay.
like a timeline that we should be following?
Yeah, let me mention something quickly about lab, thanks for bringing that up. So the way we're doing lab right now is we have 3 labs that are designed. So we had last lab, people started to make progress, set up SolidWorks. So we have the next lab, and then we have a 3rd lab. The 3rd lab, I think, is probably should be people manufacturing. So I think you should be kind of planning on the 3rd lab, so next week, manufacturing in the makerspace with Alyssa during that time. But if you're done tomorrow or you have parts ready to be manufactured, we can start on that tomorrow. But essentially we have 3 labs, and at the end of that lab, those 3 labs, you should have your motor mounts, 3 of them or more, maybe 4, like 4 motor mounts and your plates made. And then we can start assembling things. Does that make sense? So there's nothing for the next 3 labs, it's just gonna be building and designing.